Hey everyone, in this video we are solving this question from RMO 2023. It says that for any natural number n, let uh, f of n denote the sum of digits of n. F of n is sum of digits, and we need to solve the equations f of n whole square equal to m and f of m whole square equal to m. These are the two equations, and we need to find solutions to them. Okay, so first what we will do is we will prove a very interesting and important result about s of n in terms of n. We are basically trying to write s of n as like less than some quantity of n. This will help us later. Let us see what the expression is first of all. So we claim that f of n is less than 9 times log of n plus 1. Okay, so this is our claim. Now let's look at the proof. So for the proof, suppose that our n is a k-digit number. Okay, so what this basically means is that these are digits and ak, ak minus 1, e1. So these are the digits of k. This is the like notation of k, digits of n, sorry, digits of n, and n is a k digit number. So of course we can write that f of n equal to ak plus ak minus 1 plus up to dot 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 a of 1. And notice that each of these numbers is less than 9 because a digit can be at max 9. So we can write that this is less than or equal to 9 times 9 plus 9 plus 9 up to 9. And how many times 9 is there? This is precisely k times. So 9 times k. Okay. So s of n is less than equal to 9 times k. Now another fact to notice is that because n is a k digit number, so n is greater than 1, 0, 0, 0, 0, 0, and this is k minus 1 times. Okay. Because so see, n is a k digit number, and see that this entire number is the smallest k digit number. Smallest k digit number. So n is of course greater than or equal to, of course we should not forget equal to the smallest k digit number. Okay. So if we take log both sides, because log is an increasing function, log n is greater than equal to. If we take log this side, because this is number followed by k minus 1 0, this is precisely k minus 1. Okay. So what we get is log n plus 1 is greater than equal to k. And if we multiply 9 both sides, then we get that this is equal to 9k, greater than equal to 9k. And 9k is greater than equal to, as shown in our previous step, f of n. Okay, this is what we get. And so we have basically proved our result. Log of n, 9 times log of n plus 1 is greater than equal to 9k, is greater than equal to f of n. Notice that for this equality to hold, for the first equality to hold, sorry, this equality to hold, we need that n to be exactly equal to 1000 k minus 1 times. And for this equality to hold, this inequality to become an equality, we need that n should be 99999 or something like that. So basically what I mean to say is that the equality never holds. So basically this is the result we get. S of n is less than 9 times log of n plus 1. Okay, now we will use this inequality repeatedly to solve our problem. Okay, so we are given that f of n the whole square is equal to m. Okay, so now what we do is, and let's write the other inequality. We are given that m equal to s of n whole square. And notice that s of n whole square is less than 9 times log of n plus 1 the whole square. Okay, we basically square both sides of this above inequality. So we get that m is less than 9 times log of n plus 1 the whole square. Now n equal to s of m the whole square. Okay, and any number less than 9 times log of n plus 1 the whole square is less has sum of digits, like suppose we write m as s of m the whole square and is less than log of m, the same inequality applied to m plus 1 the whole square. This is what we get. 9 should be inside, sorry, the whole square. And notice that we can write that m is less than this whole thing. So basically substitute less than 9 times log of 9 times log of n plus 1 the whole square plus 1 the whole square. Okay, yeah, this is our equality. And notice that because there is a square here, wait, I'm confusing these signs a little bit. Yeah, this can be written as 9 times twice of log of 9 times log of n plus 1 plus 1 the whole square. Okay, and this 9 into 2 becomes 18, and this is exactly equal to 18 times log of 9 log of n plus 1, and the log is applied on this whole function. Okay, plus 1, and this is n. So we get that n is less than 18 times log of 9 times log of n plus 1 plus 1. Okay, now I will not prove this in detail, but this is a log like thing. Okay, so this quantity grows smaller than n. So initially this big quantity is greater than n, but as n increases and increases and increases, the first time n crosses this, n crosses the number, that is, I mean to say that if n is greater than, the first time n is greater than this big quantity, n is always greater than this big quantity after that value, because this quantity increases faster than this quantity. Okay, so using that, now suppose we substitute a value 1000. Okay, if we substitute n equal to 1000, then basically this big chunky term becomes 18 times log of, why I'm substituting 1000 is this log of n will become an easier term. This will become 3. So 3 plus 1 is 4, so log of 36 plus 1. Okay, this big term will become 18 times log of 36 plus 1, and we can easily show that. And what will be this side? N, sorry, this whole square is also there, I'm missing the whole square term both sides. Okay, and we can show that, like a bit of calculation shows that log of 36 is less than 5 by 3. How can we show this? Just take 10 to the power both sides, and this will become 10 to the power log of 36 become 36 is less than 10 to the power 5 by 3, and 10 to the power 5 by 3 is approximately some 40 something, and this inequality holds, and because of this the above inequality holds, and because of this inequality also holds, this inequality holds. Okay, sorry, this inequality holds because basically we showed that log of 36 is less than, okay, so basically we showed that log of 36 is less than 5 by 3. This is what I had claimed. And if log of 36 is less than 5 by 3, then we can multiply with 18, so this will become 30, and adding 1 this will become 31, this is 31, and 31 square is 961, which is less than 1000. Okay, so this whole term is less than 1000. This is what we concluded. So for n equal to 1000, what we get is this whole big term has reversed inequality. So this is greater than this for n equal to 1000. Okay, so if n is any number greater than 1000, then this inequality will continue to hold, that n is greater than this big term. So we conclude that for n to be less than this inequality to hold, we must have that n is less than 1000. Okay, we must have n is less than 1000, and similarly we can conclude that m is also less than 1000. So what was n initially? N was s of m the whole square. This was n, and notice that s of m whole square immediately implies that n is a square number, and similarly m equal to s of n whole square also concludes that m is also a square number. So we are only dealing with square numbers. Now I have drawn up a table. Okay, so this table shows the value of n and s of n for all the square numbers less than 1000, because we have already shown that our both numbers are less than 1000. So we must have basically uh, we look at this table and try to figure out s of n the whole square equal to m and s of n the whole square equal to n. So let's look at s of n whole square for all of this term. So if n equal to 1, s of n whole square is equal to 1, and see, the problem condition has given that m is less than n. Okay, so here if I'm writing if n equal to 1, then s of n is equal to 1. So s of n square is equal to 1 square equal to 1, which implies that m is equal to 1, which is not possible. And if n equal to 4, s of n equal to 4 and s of n whole square is 16, which is also not possible because 16 is greater than 4. And if we consider 9, then 9 square is 81, which is also greater than 9. 16 is similarly neglected. 25 is also neglected in a similar manner. 36 also neglected. 49 is also neglected. Basically we are neglecting because s of n whole square is greater than n, which is not possible because m is less than n. Okay, so 64 is also neglected in a similar manner. 81 is also neglected. And if we consider 100, okay, n equal to 100, then s of n equal to 1. So s of n whole square equal to 1. But notice that m square is not equal to s of m whole square. Okay, using that we can also write, using these conditions to simplify our calculations after this, we can write that we write m as s of n whole square, s of n whole square equal to n. This is our inequality, the whole square equal to n. So if we try to solve this inequality, we can show that after working through all of these cases, we simply check this result for all of these cases, and you will find that only 169 and 256 satisfy this condition. Okay, so 169 and 256 only satisfy this result. So using this, because m is less than n, we can conclude that m is equal to 169 and n equal to 256. This is our result. Okay, this was the solution. Thanks.